talk of the workshop today. So the talk is by, I don't know if I'm pronouncing it right, but the talk is by Rareș Ambruș. And sorry. So I hope you're able to, yeah. So just for a brief introduction, Rareș is a senior research scientist in machine learning team at TRI, the Toyota Research Institute in Los Altos, USA. His research interest lies at the intersection of robotics, computer vision, and machine learning, with an emphasis on self-supervised learning for 3D perception. He obtained his PhD in 2017 from KTH in Sweden, focusing on self-supervised perception and mapping for mobile robotics. He has over 8+ years industry experience working on autonomous vehicles, mobile robots, virtual augmented reality, and more than 25 publications and patents in top-tier CV and machine learning conferences. Go ahead, Rareș.
Great. Hello, everyone. Thank you, Ravi, for the introduction. It's great to be here at the workshop on 3D deep learning for automated driving. Before I start, can you see my slides?
Yep.
Okay, great. So as Ravi said, my name is Rareș. I'm a senior research scientist with TRI, or Toyota Research Institute. The title of my talk today is Self-Supervised 3D Vision, and basically I'm going to give you an overview of our work on using self-supervised learning to train at scale by exploiting fundamental properties in data, as well as a means to bootstrap and improve various downstream tasks. Okay, before diving into the technical details, a few words about us. So we are TRI, or Toyota Research Institute, and our mission is to develop automated driving, robotics, and other human amplification technology for Toyota. And our mandate is broad, and we have many opportunities to develop fundamental research that can be then transferred in a variety of applications. We do cutting-edge research published at top venues, including computer vision conferences such as CVPR or ICCV, as well as robotics conferences such as ICRA or IROS and Coral, with a large practical impact due to many transfer opportunities, whether for cars or for robots. And the scientific areas that we mostly focus on so far include scene understanding, self-supervised learning, simulation and auto-labeling, behavior modeling and prediction, learning for planning and control. And in this talk, I will focus on the first two areas, specifically scene understanding and self-supervised learning, with the mention that we do a lot more research than what I can cover in this talk, including across the full sensory motor stack for cars and robots, from perception to prediction and planning. So I'm going to keep my talk at a high level, but if there are questions, I'm happy to answer at the end or offline. And I will also mention that we have a $75 million collaboration with some of the best universities in the world for computer vision, machine learning, robotics, and AI in general. Okay, so diving right in, one of the topics that is quite important to us and also a very relevant scientific challenge is monocular depth estimation, or the task of predicting depth from a single monocular image. As you see, for example, on this slide, we have as input one RGB image, and we want to get the or to predict per pixel depth, as you see on this slide on the right, via a depth network. And this is inherently an ill-posed problem. We have to rely on certain priors to solve it. And as an example, humans are very good at estimating depth with just one eye, and that's because we leverage a large amount of prior knowledge about the scene. So before diving in, one question that we should consider is why monocular depth, particularly in the context of driving or robotics. And well, cameras are the most common sensors available right now, be they on mobile robots, on autonomous vehicles, on people's phones. They really are ubiquitous, widely available. And so is video data. If you think about YouTube, the large amount of videos that one can find, dash cam videos, and so on. So really very cheap and widely available. A second reason is that most platforms have complex sensor suites, multiple cameras distributed around the vehicle if it's an autonomous car, wide baselines, redundancy with respect to other sensors, LiDAR, radar, like Sunny just presented. And so it's interesting for us to learn from all of these different modalities and see if we can use one to leverage information or to transfer information to another. But it's also interesting to see how far we can push monocular-based 3D perception. And finally, in addition to it being a very important capability for any robotic system, so the ability to perceive scene depth, right, for path planning or obstacle avoidance and so on, recently monocular depth has been shown to be the bottleneck for a variety of downstream tasks such as 3D object detection. So it's interesting scientifically, but also very relevant to unlock certain other downstream tasks. So one of our key research aims is to enable robust 3D vision through large-scale self-supervision on videos. Okay, and to achieve this, what we're doing is we're exploiting the use of projective geometry as a source of self-supervision to predict dense depth of a scene from a single image. And so this is a typical output of our system. So you see the input RGB image on the left, the output depth on the bottom left, and then the point cloud that we obtain in the center. And you can see that the results that we're able to get are capture the scene geometry quite well, and not just the big flat structures such as the road, but also fine details on poles and trees and so on. And I also mentioned that we're using self-supervising in this case, not just as a pre-training task as is sometimes done, but we're actually using it to self-supervise the target task. Okay, so diving right in, I think you've probably heard the general learning architecture described already earlier today, but I'll just briefly go over it. So our first work in this direction was presented at ICRA 2019. It was titled Super-Depth, Self-Supervised, Super-Resolved Monocular Depth Estimation. And in this work, we took inspiration from Goddard's seminal work, and we designed a learning pipeline that takes advantage of stereo data at training time, as shown on this plot on the left. And the way this works is we take as input one image from the stereo pair. We predict dense per pixel depth via a neural network. And since we know the transformation between the cameras, because they're both part of a stereo camera, so we know the extrinsic information or calibration, we can perform what is called the view synthesis operation. In other words, we use the depth, the known transformation between the cameras, and recreate the first image in the frame of reference of the second image. And once we do that, all that's left is to impose a photometric loss based on the consistency between the synthesized image and the actual image, which is enough to train our network. And so in this work, our main insight and contribution was the fact that the photometric loss, which is the only cue or the only driver for learning in this setting, is bottlenecked by the resolution of the depth. So in other words, if we want to recover fine details, we need to predict higher resolutions. And so building on this insight, we designed subpixel convolutions for disparity super resolution, and we effectively replaced resized convolutions by these subpixel convolutions. And so this led to improved quantitative results as well as qualitative results, as you can see on the right side on the slide. And in the bottom, I'll play this video again. We also show, though this is not usually shown in some of the other methods, we also show the resulting point cloud, where the point cloud is rendered not from the same view from where the image was captured, but from a different view. So we can see that the resulting point cloud is quite accurate and can be used for large-scale scene reconstruction. Okay, moving on. So our first work looked at using stereo data for training, which is nice because stereo cameras are calibrated. You have two cameras and you know the transformation, which is enables us to perform this view synthesis operation. However, what if we only have monocular data at training time, which is by far the much more common scenario. And also monocular data is much more widely available on the internet. And this is the setting of our CPR 2020 oral paper called 3D Packing for Self-Supervised Monocular Depth Estimation. And in this paper, we introduced a new network called PackNet, which we also learned via the same view synthesis operation as I mentioned before. And I've also displayed the reprojection equation on the slide on the right. And in this paper, our key contribution consisted in replacing the standard pooling and upsampling operations in neural networks by learned compression and decompression modules, which we call packing and unpacking blocks. And what they do is they help preserve details which are important for reconstruction. And also in this paper, our approach was one of the first self-supervised methods to outperform supervised learning for this task. So what we noticed is that the more we trained PackNet on raw video data, the better it got, until eventually it outperformed supervised learning methods for this task. And again, you see over here the typical output of our system on the right-hand side of the slide. And I'll also mention that you can find our code and data online. So the code is at triml/pacnetsfm, models, training scripts, and so on. We also organized a workshop and a depth estimation challenge at CVPR a couple of weeks ago, titled Frontiers of Monocular 3D Perception. And those materials, the talks, are still online if people are interested in finding out more or just watching the talks or panels. And we also released a data set, DDAD, which stands for Dense Depth for Autonomous Driving. And DDAD is basically collected by the TRI fleet in the US and in Japan, and it consists of data from 6 time-synchronized cameras, along with a LiDAR scanner that is both denser and longer range than typical LiDAR scanners that can be found in some of the other data sets available. So we have readings up to 200 meters, which is nice because it enables us to estimate finer grain depth predictions at longer ranges. And in addition to that, some of the frames indeed that have panoptic labels, so semantic segmentation and instance segmentation, which allows us to do semantic class evaluation. So evaluate the depth predictions on cars or on pedestrians, which are the classes that we really care about. So that is available as well. Okay, changing gears a bit. A second task that we looked at is self-supervised keypoint estimation. And so why keypoints? Well, keypoints have been widely used to represent salient points in images. And finding and matching these key points is essential, since the associated correspondences can then be effectively used for a variety of applications such as scene reconstruction, camera pose estimation, ego motion, and so on. And so in our paper titled Self-Supervised 3D Keypoint Learning for Ego Motion Estimation, which we presented at Coral 2020 as an oral, we build on 2 streams of related work. One is self-supervised depth estimation that I've just briefly mentioned in the previous slides. And the second is keypoint work that uses, or self-supervised keypoint learning work that uses randomly generated homographies to augment input images and then impose consistency constraints on the resulting image and the original image and on the key points extracted between or from these images. And so in our paper, we extend these 2 streams of related work and generalize this learning architecture to methods that work on videos. And specifically, we proposed a pipeline for key point detection, matching, and 3D lifting in videos. And so what we wanted to get out of this work is key points that understand both scene texture and scene geometry. And the way we do this is we optimize 2 networks jointly, a key point extraction network and a depth prediction network. And to optimize these 2 networks jointly, we proposed a novel pose estimation module based on the orthogonal procrustes algorithm. And the way we do this is we use predicted key points from subsequent images. We calculate correspondences, and we regress an SE3 pose that tightly couples both the depth network and the key point network in the same joint optimization. And in this paper, we also looked at integrating our key points into state-of-the-art tracking frameworks, particularly DSO. And we got really good results, state-of-the-art tracking results when compared to other monocular methods, but also as good as some state-of-the-art stereo tracking results, which was really nice to see. And so on the images of on this slide, you see the typical output of our system. So on the top, you see the predicted key points. The color coding indicates the depth. And on the bottom, you see the predicted depth from the monocular depth network. And it's nice to see that the key points match both the camera motion or the ego motion, but also the motion of dynamic agents in the scene. Okay, so moving back to monocular depth, despite all the recent research in self-supervised learning, including our own work, most of the work in this area has focused on single monocular cameras or stereo pairs that cover only a fraction of the scene around the vehicle and that make assumptions about frontal parallelism and so on. So a question that we asked ourselves is, what if we have multiple cameras positioned around the vehicle? Can we leverage all that extra information somehow? And especially if the overlap between these cameras is minimal, so just a little bit of overlap at the edge of the images, can we somehow learn from this additional information? And this is the setting of one of our latest works titled Full Surround Monodepth from Multiple Cameras, or FSM for short. And basically what we try to achieve is we extend monocular self-supervised depth and ego motion estimation to large baseline multi-camera rigs. And so here we show an example from the new scenes data set where on each image you see some colored dots, which represent the overlap between the field of views of the images from the LiDAR. And so the way we learn in this setting is we use generalized spatio-temporal contexts, pose consistency constraints, and also we carefully designed masks for the photometric loss. And we learn a single network that generates dense, consistent, and scale-aware point clouds that cover the full 360-degree field of view around the vehicle. So really like a pseudo-LiDAR sensor. We also compare this with standard self-supervised learning methods that don't employ any of these additional constraints that we propose in this paper. And when we try to train traditional methods on multiple cameras, they simply don't work, or they perform very poorly. Okay, and in this video, we show the typical output of our system, again, with images on the left-hand side or the corresponding depth. And then in the center, you see the resulting point cloud color-coded. The color coding represents point clouds that come from different images. And it's nice to see that the point clouds are, that it's a consistent 360-degree point cloud, and that all the point clouds are neatly aligned, and they don't have different scales or inconsistencies and so on. Okay, a second common assumption, and also a significant limitation, is the assumption of a known parametric camera model. And that's usually the standard pinhole model, which leads to failure when the traditional self-supervised learning methods are applied to cameras that deviate significantly or even slightly from this assumption, such as catadioptric cameras or fisheye cameras and so on. And so in our 3DV 2020 oral paper titled Neural Ray Surfaces for Self-Supervised Depth and Ego Motion, or NRS for short, we show that self-supervision can be used to learn accurate depth and ego motion estimation without prior knowledge of the camera model. And so in this work, we're inspired by the geometric model of Grossberg and Nayar, and we introduce neural ray surfaces, or NRS, which are convolutional networks that represent per pixel rays, and that they approximate a wide range of cameras. And so the nice thing about NRS is that they're fully differentiable and can be learned end-to-end from unlabeled raw videos. So basically what we're doing is, in addition to learning a depth network and an ego motion network, now we're also learning a network that approximates the camera model and basically allows us to lift from a 2D pixel and associated depth, lift that to 3D, and then project back from 3D to 2D. And so we demonstrate in our paper that by using NRS, we can learn self-supervised learn depth and visual odometry from raw videos obtained using a wide variety of cameras, including fisheye, catadioptric. We also tested this on the standard pinhole cameras as a sanity check. And we also managed to self-supervise learn depth underwater, as you just saw in this video, which was also really nice to see. Okay, we also explored other avenues of supervision and how to combine that with self-supervised learning. And this includes semi-supervised learning, as well as sim-to-real transfer using synthetic data sets. So, and throughout our research, we found that there is a general insight or general connecting thread between these different approaches, namely that self-supervised learning enables you to make the most out of whatever little supervision you have, which is why self-supervised learning is interesting for us, not just scientifically, but also it's very practically relevant. And so in the next few slides, I'll go into a bit more details about how self-supervised learning is key for scalability when it comes to these two approaches, namely semi-supervised learning and sim-to-real. Right, so our work so far has assumed that we have only cameras, stereo or monocular, multiple cameras of whatever camera model. The next question that we asked ourselves is, what if partial point clouds are also available at training time and at inference time? And the second question that we asked ourselves is, what if these point clouds are available at inference time only sometimes, but not always? And this could be the case, for example, when it comes to cheap range sensors on some platforms, like some modern vehicles, that may be available at runtime, and they may provide some clue about the depth of the scene, but maybe they are not very reliable. We would still want to be able to use these when available, but not if they stop working or they fail. And so we recently presented a paper at this year's CVPR a couple of weeks ago called Sparse Auxiliary Networks for Unified Monocular Depth Prediction and Completion. And we show that the same model can leverage partial point clouds, both at training and at inference time, whether they're always present or only sometimes present. And this is something that we call dialable perception. And this allows our system to gracefully degrade. If one of the sensors fails, then our system is going to continue working with whatever sensors are left, which is a very important property in our applications. And so the way we achieve this is through these novel sparse auxiliary networks, or SANs, which are new models which we propose in this paper, which enable monodepth networks to perform both the tasks of depth prediction and depth completion. And the way we do this is we first decouple the image and depth map encoding stages, and then we process the depth map using sparse convolutions, which allows us to process only the valid pixels from the depth image. And second, we inject this information into the skip connections of the depth prediction network, which allows us to augment and improve its own features. And in the paper, we performed experiments with multiple state-of-the-art monocular depth estimation algorithms and networks. And we show that when we use these SAN blocks, the performance of the depth estimation task always improves. And again, on this slide, we show the typical output of our system with the input image on the bottom left, the corresponding depth map on the bottom right, and then the point cloud in the middle. And you see the output. Sometimes if the LiDAR is available, it's overlaid on the output of the system, and it aligns quite nicely, and it further improves predictions. However, if the LiDAR is not available, our system continues working just from the RGB image. Another question that we asked ourselves is, what if we have access to a pre-trained semantic segmentation network? And so we all know that labeling semantic segmentation is tedious and expensive and so on. However, a wide variety of semantic segmentation networks already exist out there and can be downloaded and used. So we asked ourselves, if we had such a network, could we use it to somehow improve our depth prediction networks? And this is the setting of our ICLEAR 2020 paper titled Semantically-Guided Representation Learning for Self-Supervised Monocular Depth. And in this paper, we proposed a novel methodology for proxy supervision, in which we take information from a pre-trained network and we distill it into another network. And the way we do this distillation at the feature level is through pixel adaptive convolutions, which are different from standard convolutions in that they allow their weights to be modified through features which are encoded or introduced from another network. And so in our case, we guide the depth network according to features from the pre-trained semantic segmentation network. And here you can see a high-level diagram of what the network architecture looks like. And also at the time of writing, we were the first to evaluate our depth predictions on different semantic classes, with results shown on the right in this slide. And we see that when we use the semantic network as guidance, we improve our predictions on all the classes. So in this plot, lower is better because we're showing ABS-REL, which is the standard depth estimation network. We're also showing some qualitative results on the bottom left. A second thing that we looked at in this paper is a well-known limitation of the photometric loss, which is its inability to model or to handle dynamic objects due to a static world assumption. And so a common failure caused by this limitation is what's sometimes referred to as the infinite depth problem. And this happens particularly if there are objects that are moving with the same speed as the camera, in which case the depth of those objects gets reprojected to infinity. And so this is a problem in our kind of applications. And so to address this issue in this paper, we designed a simple two-stage process. And without going too much into details, the way this works is we first train a depth estimation network on the whole data set. Then we run inference, and we use ransack to detect the ground plane. And once we have the ground plane, we identify the images that contain points that get projected below the ground plane. And so those are the problematic images that have this infinite depth problem. We remove them, we retrain, and then we obtain a depth network that doesn't suffer from this issue anymore, which is quite useful for us. And so on the bottom right on the slide, you see this the output of this two-stage training process, where on the left we have the infinite depth problem, and on the right we have managed to get rid of that when we train the network again. Okay, and so I just talked about how semantic segmentation can be useful for improving our depth estimates. However, as I mentioned, training semantic segmentation networks requires a large amount of semantic labels, which are tedious and difficult to obtain. And so if we can take a pre-trained network off the shelf, that's good, but maybe we want a network that works in a particular domain for our application, in which case we would have to manually label. However, instead of manually labeling, a promising avenue to get semantic supervision is simulation. However, this also comes at a cost, particularly a domain gap that hurts generalization performance. And so overcoming this gap is called solving the sim-to-real transfer problem, which is a specific instance of unsupervised domain adaptation. And this is the setting of one of our latest works now on archive called GUDA for short, or geometric unsupervised domain adaptation. And our method works by multitask mixed batch training, where we combine synthetic supervision with real-world geometric self-supervision, and we learn a domain invariant network which can predict both semantics and depth. And so you see in this slide on the right-hand side, the architecture of the system, where in Sim, basically, we have access to ground truth for all the tasks that we consider. We looked at semantic segmentation, depth, and also ego motion, and we supervise this in Sim. And in the real world, we have just videos. And then on those videos, we impose the same self-supervised photometric loss as I described in the previous slides. And we train in a mixed batch setting. And so in this paper, we show that by combining these semantic objectives in Sim with geometric objectives in the real world, we significantly reduce this domain gap. And so our network basically can transfer much better than otherwise without imposing the self-supervised loss on the real videos. We also show that the performance of our semantic network improves linearly, at least as far as we were able to test it with synthetic data quality as well as quantity. And so for this, we used a proprietary dataset, which we're currently trying to release, that consisted of 5,000 10-second videos of urban scenes, high quality, procedurally generated. And then so we generated smaller subsets or smaller splits from this dataset. And we trained and then we evaluated the transfer to the real data set, noticing improved performance. And in the image or in the video on the right-hand side of the slide, you see the typical output of our system. And you see this is running our method on real images that were not seen during training. And again, I mentioned that in this setting, our system never sees any real labels, be they semantic segmentation or depth. So it's trained purely on Sim. Okay, so in conclusion, our work shows the power of using geometry as the source of supervision on videos. And we started this talk by looking at pipelines that self-supervise directly the target tasks, such as depth, ego motion, self-supervised keypoint learning. And then we went beyond that to what we call self-supervised plus or scalable supervision. We're looking at how to combine self-supervised or self-supervision with semi-supervised learning, as was the case in when we have access to sparse LiDAR readings or semantic segmentation. And we also looked at how to use self-supervised learning to improve sim-to-real transfer in order, or in other words, how to learn in the matrix and then transfer what was learned in the real world. And so if you're still not convinced that self-supervised learning is interesting, I will leave you with Alyosha Efros's famous quote saying that the AI revolution will not be supervised. Thank you for your attention.
Thank you for the talk, Rareș. Do we have any questions? I think there's one already in the chat.
Right. When can we expect to see the FSM paper training scripts in GitHub? Oh, yeah, we're working on that. I'm not sure I can give you a timeline right now, but should be in the next month or 2 months. we recently, so as I mentioned, we recently presented the sparse auxiliary network work, and that has been released. So we presented that 2 weeks ago at CVPR, and that code is available with the network and the training scripts. Yeah.
So I had an open question. I mean, I think that this was already a quite dense talk and overview talk. So I was wondering if there are any other self-supervised tasks that, besides the depth task, that would help in 3D object detection. So for now, this has definitely a strong effect or a sort of inductive bias on the generalization for 3D object detection. Do you see any other tasks that could actually correlate with 3D object detection?
Right. So we looked mostly at self-supervising depth, ego motion, key points. I think another task that I've seen works on is traversability, or road detection, or like a free space detection that can also be self-supervised. Self-supervised normal estimation is also part of the same family of concepts, I would say. In addition to that, of course, there's all the self-supervised learning work that tries to learn a representation that can then be that is better applicable to a downstream task such as 3D object detection. We also have some work that we are going to put on arXiv very soon on how to use self-supervised learning or like raw data to improve 3D object detection, where we got some really good results. So that should be on arXiv in the next week.
Perfect. Thank you.
Thank you.
Hi, I have a question.
Yes.
So a great work on monocular depth estimation. It was really
thank you.
Awesome papers, I would say. So what can you explain what would be the limitations of monocular depth estimation, as there are like a stereo based, or now recently the radars has been popular for the high resolution. So can you please explain or express in your comments?
The limitations. Okay, so right. One of the limitations that we have tried to address was that infinite depth problem, right? So when you're purely self-supervising, if you make no assumption about what's in the scene, that's nice because you can learn from all the data. However, there may be these objects that move at the same speed as the camera, and then you get this infinite depth problem that can be quite a nuisance, and that we managed to solve using this two-stage learning problem. The other one other issue potentially is how do we transfer to unseen situations. So, for example, most of the data sets are collected in certain regions and just in certain times of the day. And so how well does that work at night, or in snow or rain? These are the kind of things that we're looking on right now that we still haven't been able to solve. But of course, if you have a stereo camera, then the performance is going to be better because a second camera is going to provide you more information about the scene. And so that implies that by using the second camera, you should be able to get better results. Yeah, I haven't worked with radar yet, but I would be very happy to see a data set of radar and LiDAR that we could try these things on.
Nice. Yeah. Thanks for that.
Thank you.
Additionally, did you ever face like a challenge where the camera settings has been changed from training and then the validation, or let's say training and then the test scenes? So could that be a challenging problem?
Yeah, that is a good question. Of course, these networks tend to overfit. There's an interesting paper that talks about how these networks learn, and the findings are that basically the networks learn to correlate appearance with depth. But they also overfit quite significantly to the camera model or the camera parameters. So there's work that tries to learn that model, or the delta to the pinhole parameters that you start with. In our own work in NRS, we basically forget about the camera model and just learn a new camera model from scratch, which allows us to basically just train on pretty much any camera. And we've even tested that underwater, and we were able to learn depth, which was pretty cool to see. So yeah, that if not addressed, then that can definitely be a problem.
Yeah, thanks a lot for the answers. It was really
Thank you. Thank you for the question. I see there's one more in the on the chat. So could you say something about real-time performance? Yes. So PACnet is a slow network, large network. We have shown that it generalizes better than networks that have similar capacity. So for example, a ResNet 101 or a ResNet 151. However, we have faster versions of PACnet, and we have implementations that can run almost real time, I would say.
I have another question, that is,
Okay.
was wondering if there was a presence of a landmark object, which is a 3D object, in a sort of a 3D map representation, would you be able to use this as prior information to correct the depth estimation? For example, I have a car that has been geo-registered, and I know the 3D model, and I give you the CAD model. Would you be able to use this in your self-supervised framework?
Right. So that, I think then we're learning in the semi-supervised setting, in the sense that we use some form of supervision, and typically we would use LiDAR. But if we know exactly where we are with respect to a map, then of course we can use the position of the car or the dimensions and so on to bootstrap learning. I think the nice thing about self-supervised learning in its purest, rawest form is that you can just basically use all the videos that you have. And our experiments with PACnet, at least, show that the more data you have, the better the results. And that doesn't require any additional sort of, map information, or, of course, there are limitations. So when you learn in the purely self-supervised setting, the depth predictions are inherently unscaled, which they're not when you have stereo cameras, because you know the baseline and you know the metric quantity that relates to cameras. And there are ways around that also, which we have addressed in some of our papers.
Yes. Thank you.
Okay, I see there's one more question. Comment on solutions to tackle reflections on glass surfaces for monodepth. So that we haven't really looked into that. Neural ray surfaces can address some of these effects in the imaging sensor, right? So if we have cameras that are not well calibrated or have distortions, or underwater where the water itself distorts the image, we have noticed that through NRS that can work. I guess it depends on how severe the reflection is, but I would definitely try NRS in that kind of setting to see how it performs. We have managed to learn, as I said, underwater, which was really impressive. We have also managed to learn on uncalibrated cameras with some amount of distortion, where we just could not learn with the traditional self-supervised learning paradigm, where we make an assumption about the camera model. So I'm not sure if that answers the question, but that's my best answer right now.
Do we have any more questions?